having done all those oral histories, I feel one of my roles here tonight is to represent the folks who made major contributions in non-volatile memory, but are not sitting on the panel tonight. So we're starting here with Dawen Kang and Simon Z. The floating gate is the fundamental piece of technology that has sustained and scaled the non-volatile memory industry from a germ of an idea in the late 60s to where it became the biggest and most important semiconductor memory device in all history. And it started, interestingly enough, with a lunch date in the labs at Bell Labs in Murray Hill. Dr. Z had started working there and joined up with his slightly older colleague, Dr. Kang, and Dr. Z had previously been doing some work in at university area in trying to do what would have become non-volatile memory, but he never got there. And at Bell Labs, the two of them were thinking about could they possibly replace core memory with some sort of solid state device that didn't take up as much room and use as much power. Well, one day at lunch, they were thinking about that, and at the same time, Kang was a little bit hungry after lunch and said, "I'm going to get some more to eat," and he brought back a piece of cake.
Cheesecake.
It was either cheesecake or some other cake, according to Dr. Z. Anyway, looking at the layers of the cake with frosting in the middle, he said, "You know what? We heard that we could do tunneling through thin layers." And he thought, gee, maybe we could make a floating gate. And they set their mind to it and eventually demonstrated a floating gate device which could hold charge. The net result was that the powers that be at Bell Labs abandoned it. They said, the bosses in that lab said, "It'll never work, it won't have any use for us," and they just said, "We wrote a paper, can't we present it at IEEE? No. Just publish it in the Bell Labs Technical Journal," and that's what they did in 1967. Others had eventually got to see it and use it. So that's the story of Simon Z. He later stayed 27 years and worked on many projects at Bell Labs. Ultimately retired, became a professor at the National Taiwan University, where he had studied as an undergraduate, and ultimately also as a visiting professor still today in his 80s at Stanford University.
Actually in Taiwan, though?
Both.
Both, that's right, but Stanford and Taiwan?
Yes.
Okay, thank you.
Enough of that slide.
Enough of that slide.
Here's another one that isn't on our panel anymore. Charles C. Unfortunately died several months after I took his oral history. He died in 2013. He also an immigrant coming to the U.S. to study, had been born in Shanghai, studied in New York City, and ultimately took a job after graduation with IBM in their research labs. He was there working on thin film memories, which were magnetic. And after a while at IBM, his first job was at RCA, by the way, and he moved over to IBM in order to work on thin film memories. He took a leave of absence to go get his PhD at University of Iowa, and there his advisor had told him, forget about magnetic memories, go for something solid state. And he started working on how he could make a solid state device that could store a bit of information and also unstore it at will. Ultimately, after many experiments, he came up with a chalcogenide amorphous material, a glass material, which is clearly an insulator, but was able to demonstrate the growth of a crystalline low resistance filament through that insulator in a very narrow space. And he constructed a demonstration module which had 2 layers of metal with the sandwiching this amorphous material, and by applying a voltage through it, he could cause that filament to grow and turn it into a low resistance conductor, and also to ungrow the filament as well. So it was infinitely changeable, and it was the first phase change memory. Now, again, his company never built it, but he did publish papers on it, and ultimately he joined with Obshinsky and worked on phase change memories in the 70s, and spent after that most of his career at Xerox, where he retired as a senior vice president. And therefore, we have the origins of both floating gate and phase change memory, both from the Chinese immigrants coming here and doing their thing. So let's hear it for the immigration policies.
Indeed, and both in the late 60s.
Yes.
Yeah.
And both of those were done, but not ever turned into products before other companies did do and got famous for doing commercially successful non-volatile memory. Next.
Great.
And one of the founders of Sundays also is Chinese.
Indeed. Thank you. So now in 1970, with the invention of the EEPROM and Dov Fruman, and you also did
My cue again. Yet another immigrant who came in from a foreign undergraduate to get a U.S. graduate degree. Dov Fruman, having graduated with his master's in EE at Berkeley, took a job at Fairchild and was invited to move with the Fairchild people to start Intel, but he declined because he was in the process of completing a PhD in metal hydride MOS. Nitride MOS, that's what, that was a non-volatile MOS that used a thin film of nitride to store or pass through its charge. He wanted to do research in that and did, and completed his PhD, at which time he started at Intel in '69, I believe it was. And he had little to do with nitrides at Intel. They didn't want to do that. They had too much on their plate already as this little startup. So they asked him to help work on debugging a reliability problem that they had on the 1101 MOS static RAM, one of their early products. It turned out that it works fine in the lab or in the test, but as soon as it got out into the field where there was high humidity, it was failing. And they put it in the humidity test at 85 and found out, yes, there was failures, and he had to go identify what it was and produce a cure for it. In identifying what it was, he noticed that the oxide on which metal had been deposited was contaminated by the metal, and the metal had been activated by high humidity, the metal on that oxide, and caused the oxide, which is normally an insulator, to conduct. And it was allowing charge to leak off their gate inadvertently. And so he said, hey, what if I can do that on purpose? Make charge go through the insulator. And so that's how he came up with the first EEPROM. And it took, again, a number of experiments, and he credits in his oral history that he got by very easily because the rest of the company wasn't worried about that. They were worried about their other problems, and they left him alone. And he went and he kept experimenting and experimenting until he got reliable ability to use avalanche hot electron injection to charge up a floating gate. Now, the original floating gate had been done with metal gates, but Intel at the time was using silicon gates, and his technique worked for that as well. And then he had to realize how he could erase it, and that was with a high energy of UV light. Okay, so that was the first EEPROM, and that needed a quartz glass for the UV light. It's very expensive. He didn't think he'd be able to make it, but Noyce allowed him, having seen him one day in the hall, feeling very dejected. What's your trouble? I don't think this thing works, but I don't think I'll be able to get the packaging and production people to deal with this quartz window idea. And Noyce said, go ahead and do it. So he did. And that became a successful product and actually helped to fund a lot of Intel's later developments. It was sold initially with the 8008 micro. I think I'm almost done with these.